Welcome back, class. Like I ended on the last video, we are now going to go through pyrrole and pyridine and look at how they're aromatic and when do you count the lone pair electrons on the heteroatom and when do you not. So let's start with pyridine. Now let's go through the Huckel rules. Okay. Is it cyclic? Yes, it is. Is it planar? Are they sp2 hybridized? Every atom in here is sp2 hybridized, so it's going to be planar. Check. Do we have conjugated pi bonds? If they're sp2 hybridized, then they're going to have sp2, or if they're sp2 hybridized, then they're going to have p orbitals. Okay? And every atom has a p orbital. Now, does it follow the 4n plus 2 rule? And like I mentioned last video, here, do you count the lone pairs or not? Here's the trick. If the heteroatom has lone pairs and there's a double bond attached to that heteroatom, you do not count the lone pair. So we can see that there's 2, 4, 6 pi electrons, aromatic. Let me I'll say that again. If the heteroatom with the lone pairs has a double bond directly attached to it, you do not count the lone pair. Now let's look at pyrrole and contrast that. Erase that. Okay, lone pair. So if we go through the checklist for pyrrole, we'll see that it is in fact cyclic. Every carbon right here is sp2 hybridized. How do I know that this nitrogen is sp2 hybridized? Because it looks like there's 1, 2, 3, 4 groups. So you might think it's sp3. But remember from class, we have resonance. Like that. So that nitrogen is in fact sp2 hybridized. So every atom is sp2 hybridized, so we have a conjugation of p orbitals. Now here's the trick. Do we count the electron, the lone pair, or not? Well, when you look at this structure right here, do you see how there's no double bonds connected to the heteroatom when there's a lone pair present? When there's lone pairs present and no double bonds connected to the heteroatom, you do count the lone pair. And so it will follow Huckel's rule. There's 2 electrons here, 4, 5, 6. So the same answer here. So pyrrole is aromatic and you do count the lone pair on the heteroatom. So that's the trick right there. If the heteroatom has a double bond attached to it, do not count the lone pairs. But if there's no double bonds attached to the heteroatom while there is lone pairs present, then you do count them. Okay? When you come over here, you do see that this nitrogen has a double bond attached to it, but there's no lone pairs. Okay? Now, so that's the trick, but let's talk about why. Why do you count the lone pair versus not? Well, it just has to do with where are the lone pairs present. What type of orbital? Is this lone pair in a p orbital or an sp2 orbital. And you can see on my slide right there that the lone pair on pyridine is in a sp2 hybridized orbital. And then when you look at pyridine or pyrrole, you can see that the lone pair right here, shown in red on my slide, is in a p orbital. That's what is happening when you look at the molecule. Where are those lone pairs going to be? What orbitals? Okay. Now this is an interesting slide in which is looking at pyrrole. And it's looking at how basic pyrrole is. Oftentimes, nitrogens in species are pretty basic. Okay. But pyrrole is not very basic, because when you look at the slide there on the left, you see pyrrole with the lone pair. And then it goes and abstracts a proton from an acid represented by HA. And then what happens to the aromaticity of pyrrole when it accepts that proton? It becomes non-aromatic. So pyrrole doesn't act as a strong base, because if it did, it loses aromaticity, loses that stability. So it's not basic or very basic at all. And you can see that from the pKa. But when you look at pyridine, on the other hand, these lone pairs right here are used as a base to abstract a proton from an acid, because if it did use these electrons right here to abstract a proton, does it lose aromaticity? And you can see before it grabs the proton and after it grabs the proton, they're both aromatic. And so pyridine is basic, and it can act as a base. I think that's so cool. So it can use the lone pair, can't use the lone pair. Here's some examples of just much larger molecules. We call them polycyclic aromatic compounds, and they are as well aromatic. And I just wanted to bring that to your attention. Have you ever been to, well, for me, when I visited my grandparents, they would have mothballs around their house, and it just had that unique smell. That is anthracene, the smell of mothballs. Or it's naphthalene. Now I'm doubting myself, but it's one of those two molecules is the smell of mothballs. I'd have to double check on that. Okay, now we're going to delve into some reactions now. We're going to review some Orgo-1 reactions, and then we're going to see and learn some Orgo-2 reactions after we review that. So I'm going to clear off this board so we have lots of space to write. When we have a benzene molecule and we have carbon atoms attached to it, as you can see represented by the red arrows, there's carbons attached to that benzene ring. The carbon that is directly attached to the benzene ring is called a benzylic carbon. And benzylic carbons are really important because they're reactive and they're going to react in a certain way. So whenever you look at a benzene, it does not matter what the carbon necessarily looks like. You know, it could be any group attached to it. The benzylic carbon is going to be the one that is directly attached to that carbon. So this one right here is directly attached to that benzene ring. So this one right here that I circled is the benzylic carbon. It can look however the carbon chain wants to be. Now, in review here, if we take benzene and treat it with chromic acid, nothing's going to happen. There's no reaction. If you take a simple alkane and treat it with chromic acid, nothing happens. Okay? So benzene and alkanes are not readily oxidized. They just don't. They're very low in energy and stable towards those oxidizing agents. Now, what's interesting though, if you have a benzylic carbon on the benzene, it does react with chromic acid, as you can see there in the slide. So it takes a benzene with an alkyl group attached to it, and it can oxidize it into a carboxylic acid. But just reiterating, this is very, very important. There's no allylic carbon, or benzylic carbon in an alkane, so there's no reaction. Now, I just said that if you have a benzylic carbon, you will treat it with chromic acid and it will turn into a carboxylic acid. There is an exception that you have to be very well aware of, and that is if the benzylic carbon has no hydrogens, it cannot react. And the mechanism for how this reacts is debatable. It's very complex. You don't need to know the mechanism. You just need to know the final result. If there is a benzylic carbon that has at least one hydrogen, it will turn into a carboxylic acid. So this molecule right here, would it react with chromic acid to turn into a carboxylic acid? Well, you just have to analyze it. There's the benzylic carbon. Is there a hydrogen on there? And lo and behold, there is one hydrogen. So this molecule right here, treating it with chromic acid would in fact give us a carboxylic acid right there, or benzoic acid. So that's a key thing to remember, that rule. You have to have at least one hydrogen. Okay. There's another reagent that you can use to oxidize benzylic carbons, and that's permanganate. But with permanganate, you have to do it in 2 steps. You treat it with permanganate, you heat it up, and then it will generate the carboxylate intermediate. And then you just do a acidic workup. That's what the H3O plus is. That's the hydronium ion. So that's implying that you're adding an acid and doing an acidic workup to protonate that carboxylate to turn it into the carboxylic acid. So overall, it is the same. You get the same product when you take a molecule with a benzylic carbon and treat it with chromic acid. You would get this. If you treat it with permanganate and an acidic workup, you'll get the same product. The same rule applies though. With permanganate, you have to still have at least one hydrogen on the benzylic carbon. That is a requirement. Big, big requirement. But when you look at using permanganate to perform the oxidation, we have some additional things that we can look at, which is kind of cool. And I still probably have some labs whiteboard space here. Let's look at this. So this rule right here where I said the benzylic carbon has to have at least one hydrogen. But with permanganate, we're going to expand that. So if this carbon right here has a pi bond, it can work as well. So let me show you what I mean by that. So if we have this compound right here, do you see that this benzylic carbon right there has p orbitals, or a pi bond? That's what I want to say. You're looking for the pi bond. If it has a pi bond and you treat it with permanganate, potassium permanganate, and do the acidic workup, what product are you going to get? You're going to get the same product here. You're going to get the carboxylic acid. So what about if we had a molecule that looked like this? Would that react and turn into this product right here? Yes, it will, because you see that you have a pi bond on that carbon right there. So it'll work. What about, let's draw it right here, okay? Let's look at another molecule here. What if we had, oh, you can't see that very well. So let me just use this one. What if you had that guy? What's the rule? Does it have pi bonds? So that does, in fact, react with permanganate to turn into the carboxylic acid. Do you see how this carbon right here doesn't have any hydrogens? I'm expanding the rule. When you use potassium permanganate, it either needs a hydrogen or pi bonds, and that will react. All right? So free radicals and doing bromination, this is a orgo-1 reaction. So this is going to be a slight review. So I'm going to pause this so I can clean up the board so we can do some reactions here. So from orgo-1, do you recall radical brominations with alkenes? So if I had an alkene, and let's say I treat it with NBS, and we add a little bit of heat, do you recall what the product is? Do you recall what NBS is? N-bromosuccimide. N-bromosuccimide looks like this. That's N-bromosuccimide, and it's basically a bromine source. So it's really just going to give us some bromine. That's what its whole purpose is. So do you recall, when you take an alkene, treat it with N-bromosuccimide, what is our product going to be? Is it going to be that product or this one? This pen is kind of getting worn out. So I would pause the video and just kind of think about it. Do you recall what the product's going to be? Is it this top one or this bottom one? Well, it is definitely this guy right there. That is the product. So if you go back to your textbook, you'll recall in the mechanism, you're going to get this intermediate right here, where you're going to get a radical. And that right there is called an allylic radical. And that's a relatively stable radical. And then this radical right here is then going to be used to help form a bromine carbon bond. Okay. So the reason why I'm bringing this up to your attention is because the benzylic carbon kind of behaves like the allylic carbon in the radical brominization of alkenes. So if you look here, if we take benzene with a substituent with the benzylic carbon there and treat it with N-bromosuccinimide, you're going to add the bromine to the benzylic carbon. Okay. Now, why should you care about these things? Well, because when you have a, let's change this molecule here. All right. Why is this so important? Well, because now you have a bromine on the benzylic carbon, and now you can do SN1 reactions, SN2, E1, E2. What's happening is we're putting a group on there so that we can do additional reactions. That's why this reaction is so powerful, because it gives us useful intermediates in a synthetic route. So in the slides that I'm going through now, you can see some of those examples. We have an SN1, we have an SN2, E2, and E1. So that's the driving force of learning this reaction, is because it generates really good intermediates. Okay. So this slide right here is a very useful slide to review, because it's going to show you the it's summarizing very useful information with benzene derivatives. And then it's showing you when you convert, let's say, your benzene derivative into those alcohols shown on the right. Now we have alcohol chemistry that we have to remember. And this slide shows you, you see chapter 12, chapter 8, it tells you the reactions that you can use with alcohols and alkenes and just all sorts of stuff. So that's all review that I would highly encourage you to make sure you understand. Okay? But we don't have time here to go over all those reactions again. So we talked about oxidation of the benzylic carbon. Now let's talk about reducing benzenes. Okay? Now in that slide you see the benzene with 3 moles of hydrogen gas with a nickel catalyst and very high pressure and very high temperature. We can force benzene to be reduced. What does it mean to be reduced? The simple answer to that question is when you add hydrogens across a double or triple bond, you are reducing it. And we can reduce a benzene, but it takes a lot of effort. Just think about that for a minute. We live at approximately sea level, so that's 1 atmosphere of pressure. In order to get this reaction to work, we need 100 times more pressure. And we need a very elevated temperature. So those are really harsh conditions. But if you have, let's say, styrene, that benzene molecule at the bottom, let's just draw it here so we can make sure we know what we're talking about here. Okay. So I'm talking about this molecule right here, styrene. Now what's cool about styrene is that we have the aromatic ring, and then we have this alkene right here. That's not part of the aromatic ring. So what we can do is we can selectively reduce this double bond, but not reduce any in the benzene ring. And so how do we selectively do that? We adjust the conditions. You can see that the conditions there are changed to only 2 atmospheres of pressure and only 25 degrees C. And so those conditions will only touch and reduce that alkene. Very, very important reaction that's very famous. It's called the Birch reduction. And a Birch reduction takes a benzene ring and reduces it slightly. You can see in the slide there, you know, it's really hard to, let's just draw it here. When you take benzene and treat it with sodium metal and some methanol and ammonia, what do we get? We get that compound right there. And what has happened? Those carbons right there have been reduced because we have added some hydrogens there. You can see that there are 2 hydrogens coming off. Okay, so we added hydrogens, so it's been reduced, but we did not reduce these carbons right there. So in order to understand the Birch reduction, we're going to need to go through the mechanism to understand what's going on here. Okay? So I'm going to pause the video and clean up this board. Now another thing to note in the reaction conditions here, the sodium is a solid metal, the methanol is going to be a liquid, and then we have ammonia, which is NH3. That is also going to be in the liquid phase. Now when you take sodium metal and add it to ammonia, you're going to dissolve the electrons. And you're going to basically get like free floating electrons in the solution. So that's kind of how I'm going to represent this when we look at benzene here. Okay. So when we take the solid metal, put it in the ammonia and the methanol mix, we're going to just generate, I'm just going to call it electrons. Okay. And so what happens is that one electron is going to come and add there. Okay. And then we go like this. Do you see how I'm using fish hook or single hook arrows? The single hook arrow is telling me that 1 electron is going. In contrast, if we had something like this, and I go like that, 2 arrows, that's saying both electrons are moving over there. But with the single fish hook, only 1 electron's moving. So I'll show you what that looks like. All right. So this is a radical addition step right here. Radical addition step. And we are going to now have 1 electron here, and then 1 there, and that one. So we're going to have 2 electrons right there. So that's going to give us a negative charge right there. Now the purpose of the methanol or alcohol is it's a proton source. All right. And you can't see the proton. So let's draw it right here. Now, this bond angle right here, that's not correct, okay? Because that's a sp3 hybridized, so the bond angle should be 109.5. But I'm just drawing that because I ran out of space, okay? So what happens here? It's going to act as the proton source. So the lone pair here is going to come and grab that proton to reduce that carbon. So now we have added a second hydrogen to that carbon. We still have the radical right there. And then what are we going to have left over? We're going to have the alkoxide left over. Okay. Now the next step, right here, is we're going to have a lot of these dissolved electrons in the solution. So that electron's going to come right there and give its electron to this radical right here. Okay. So that's going to then give us a negatively charged carbon right there. Now, this right here, okay, can have 3 resonance structures that I want you to pay close attention to, okay? These resonance structures are important. And let's draw the resonance structures. Okay. And then let's see if we can find some room here. There, that works. Like that. Now we still have that hydrogen that was added. Okay. Now let's show the reaction arrows of what's happening here. So we have 3 resonance structures. I'll label that guy X, Y, and Z. We have 3 different resonance structures. Now, let's show you the mechanism here. So this lone pair right here is going to come down, and then those are going to go there to give us this species. That's not right, is it? There, to form that double bond and that give us that lone pair. And then go to the Z resonance structure, what's going to happen? That lone pair right there is going to come down, form that double bond, and like that. Okay? Now in this mechanism, you have to pay very close attention. We have double hooked arrows and single hooked arrows. They mean different things, and it's really, really important. Now we have these 3 different resonance structures. When you look at them, could you identify the most stable resonance structure and why? Okay. So I would pause the video and think about that. Which structure would you select as the most stable resonance structure and why? The answer is it is molecule or resonance structure Y. That is the most stable resonance structure. And the answer is quite simple when you compare X and Z. When you look at X and Z, let's focus on X. Do you see how this lone pair only has one option? It can only go here. Could that lone pair come and go right there? No, because if it did, it would form a Texas carbon. Because remember, there's that orange hydrogen right there was already there from the beginning. So this orange hydrogen was this one right there. So we already have a hydrogen that was there. Okay. And then this green hydrogen that was added came from the methanol. So this lone pair cannot come back and go here because then you would form 5 bonds, and that's not good. Same idea with this one. This lone pair can only come, and you can't see that lone pair. I'll draw the lone pair right there. All right. So this lone pair on this carbon, this lone pair only has one option. It can only come and go right here. So like this, all right? It can only go there. But look at Y. This lone pair could resonate to the right, and it could resonate to the left. It has more options. And when electrons have more option of movement, more freedom to move, it lowers its energy and becomes more stable. So Z and X only has one option to resonate, whereas Y has two, making that the more stable structure. Okay, and now when we're in this resonance structure right here, let's clean up these arrows to see the next step. So we'll take, this was what structure Y, and we're going to need some more space. So what we'll do is we have our methanol right there. And so we can take this lone pair right here, and it's going to come and do a proton transfer to give us our product. And that is the Birch reduction. So if you have the thought, why do you have this orientation of double bonds? Why does it look like this? It comes back to the mechanism, and when you look at the three resonance structures, is because this resonance structure is the most stable, which then leads to that product. That is why you don't get a product that looks like this one. Compare that. Compare A to B. They're isomers of one another, right? I'm getting really bad at drawing stuff that you can't see. My apologies. So let me draw it again. What if we did a proton transfer and gave you this as your product? So that's molecule A, that's molecule B. Now compare the two. Why is this the Birch reduction product? It all comes back to the fact that it comes from the more stable resonance structure. This product is not formed because this resonance structure right here is not very stable. So I hope you're seeing the power of a mechanism and how it helps you and I predict stable compounds. Or it helps us to understand when we observe a reaction and we do a Birch reduction, we don't get any A, but we get B. We're like, why is that? There's the answer. Now let's take a benzene derivative with the Birch reduction conditions, but now we have an alkyl group. And that's going to influence the regiochemistry here of these double bonds. So if it was me learning this for the first time, I recall that a Birch reduction was simply where you take a benzene ring like this, treat it with these conditions, and you get this semi-reduced molecule, right? That's what we learned previously. So if I did this reaction, now the only difference is I have an alkyl group. I would suspect that this is the major product because it resembles this, right? But it's not. This guy is not formed. All right. This alkyl group is going to influence the reduction. Recall that alkyl groups are electron donating. Okay, and when it donates electrons in, it's going to, you'll see in a moment, cause some problems. So, the reason why this is the major product has to do with the mechanism, and I'm not going to show you the whole mechanism, but there's going to be a intermediate. Okay. So what I'm drawing here, make sure I get this right, in order for us to get this as the major product, we would have to have this intermediate. To see how this carbon right there has a hydrogen and it's been reduced. So our goal is to get a hydrogen here. And the only way to get a hydrogen on this carbon is to have this intermediate. But you see how this intermediate is going to lead to there. But this intermediate does not form, hence we don't get this product. Why is this intermediate so unstable? Well, it comes back to the idea that R groups are electron donating. So it's going to put in electron density into the ring. Now you can see how that's going to be a problem. Already have lone pairs here. That's a formal charge of -1. Electron density being pushed closer to more electron density. That's repulsive. That's just too unstable. So this intermediate does not form. And that's why we don't get this as our product. We get this one over here. Now, what if we change this up a little bit? Let's change this R group. Let's change that R group to ketone. Right. Right there. Now you can see the ketone is now an electron withdrawing group. Why is it an electron withdrawing group? Well, resonance helps us to understand that. Do you see how those pi electrons can go there and there? This group right here is pulling electron density away from the ring. And so that has a difference now in which this is now going to be the product. And this one is going to be not formed. Now in this one, notice that these two carbons have been reduced. Now in order for that to occur, one of the intermediates, we've got to clean this up, would have to be this guy. All right. And now that you have an electron withdrawing group here, you have your anion. To see how that anion can be somewhat stabilized from the electron withdrawing ability of this group right here. And so this intermediate is stable, which then leads us to this product. So the moral of the story, alkyl groups are electron donating. And if you have an electron donating group, you're going to get this version. Okay. And if it's electron withdrawing, with these, this is an electron withdrawing group, you're going to get this as your major product. Okay. So we have regioselectivity here. So the remainder of the slides that you have at your disposal is going to be going over spectroscopy. And I'm not going to focus our time on learning that because we've already gone through the spectroscopy chapters. But this is still important to know. Just because we've had an exam on spectroscopy doesn't mean it won't pop up again. So I'm just not going to lecture on it, but you do need to keep fresh on top of your spectroscopy skills because that's just never going to go away. You can just see here some examples, some NMR and how it all works. And we discussed and learned about this in previous chapters. Okay? So that is it for this chapter and for this video. So if you guys have any questions or concerns, as always, I'm more than happy to help. Just reach out.